Okay, I think I finished up last time talking a bit about entropy, the Carnot cycle, and one last thing I want to talk about is the temperature scale. So this is on number 2 here. The very end is the International Temperature Scale. Okay, just the definition of temperature. I think this is important too if some of you are working on optimizations and reading literature from the past, is exactly what is the temperature. Remember I talked about a Carnot cycle. It's an ideal cycle, but in principle you could really do it. Here you have 2 isotherms, and here you have 2 adiabatics. You go around the cycle, 2 isothermal paths and 2 adiabatic paths. And I said up here you have Q1 over T1. This is reversible, so Q1 over T1 is the entropy change up here. And on this path here you have Q2 over T2. So this is delta S prime, this is delta S double prime, and the sum of delta S prime plus delta S double prime is 0, because S is a state property. Okay, so for any Carnot cycle, Q1 over T1 equals Q2 over T2. And so I showed that's true even if it's not an ideal gas in the Carnot cycle. Now what this means is, well, what is temperature? This means is that, as I said, it is possible to define a temperature scale such that this is true. This is what Carnot showed. So for instance, if you were to build a Carnot engine, ideal reversible Carnot engine, and you put the cold reservoir in, say, ice water, and the hot reservoir in boiling water, so you're at 273 and 373 Kelvin, and you measured the ratio of the 2 heats, Q1 and Q2, you would find that they were in the ratio 373 over 273. This over this has to be equal to this over this. So you put this in ice water, you put this in boiling water, and Q1 over Q2 equals 373 over 273. Now you have defined your temperature scale. Now any other temperature, this is what Carnot showed, any other temperature then, if you put this in a higher temperature and you measured Q, that would tell you what T was. Okay? So that's the Carnot thermometer. This also, by the way, gave the hint to Carnot and the boys that there was an absolute 0. Okay? I mean, what happens when T goes, there must be an absolute 0. This is 373 over 273. When this goes to 0, you'd have 0 over 0. So they had this idea that there was an absolute temperature scale, which basically was kind of discovered by this argument, but they didn't, at the time they didn't understand what absolute 0 meant, but now we do. So anyway, that's the Carnot engine, the Carnot cycle. So if you, in principle then, this defines your temperature scale. You put this into another reservoir, you measure Q, and that tells you what T is, because it has to be equal to this Q2 over T2. So in principle then, we could set up a temperature scale by building a Carnot engine and putting it in the room and running it and finding out how hot the room was. Obviously this has immense practical problems, but this is theory. Now what I did on Tuesday too, however, I showed you that if you put an ideal gas in here, and you have an ideal gas temperature, PV is nRT. Or let's put it the other way, the ideal gas temperature, T, is defined as PV over nR. So if I take an ideal gas, an actual gas, say I take argon or helium, I put it at a high enough temperature and a low enough pressure, it's going to be ideal. I measure pressure volume, I know the number of moles, that defines what the ideal gas temperature is. So I can build an ideal gas thermometer. I take a great big bulb, very big bulb, where the volume is known. I put this in some sort of, I put a known number of moles of gas in the bulb. I put some sort of a manometer here to measure the pressure. So I measure the pressure, I know the volume, I know the number of moles, and I determine what the temperature is. So this is an ideal gas thermometer. Okay, now I did the argument yesterday, though, or Tuesday, that if a substance obeys the ideal gas equation of state, then I showed Q is nRT log PV log P2 over P1, and then Q2 is nR2 log V2 over V2. So this was part of the Carnot proof, that if in here you put an ideal gas that obeys this equation of state, then this automatically follows. Now we know what Q1 and Q2 are, and we find that, in other words, this is called the thermodynamic temperature scale determined by the second law. the thermodynamic temperature scale and the ideal gas temperature scale are the same. So this is now more practical, because it's more practical to build an ideal gas thermometer. And this in fact is done. They build ideal gas thermometers in the past anyway, and you can measure very accurately, not very accurately, you can measure the temperature, and that as long as you don't have a very high pressure. You have a high enough temperature or a low enough pressure, that defines the ideal gas temperature scale. So the ideal gas thermometer is sort of the thermometer of choice that defines the proper temperature scale. Now why do we want to have a proper temperature scale? Well, otherwise the second law doesn't work. Delta G, delta H is no longer negative for every spontaneous process and so on. Okay, then thermodynamics doesn't work. So you could say, why not just define any temperature scale? We make ice water goes at 0 degrees and boiling water is 100 degrees, and in between the two we build a mercury thermometer and assume temperature is linear with it, and it just say the melting point of gold is 1500, why not, and picks a few points, and then the thermodynamics would work. You have to obey it has to be the thermodynamic temperature scale, or else when you went around a cycle, delta S wouldn't be 0, S would no longer be a property of state. So we have to use the thermodynamic temperature scale for thermodynamics to work. The thermodynamic temperature scale is the same as the ideal gas temperature scale, so this is the thermometer of choice, but obviously this is not terribly useful either. But you could do it. But what you do is we use this then to calibrate various secondary standards. Okay, so well, first of all, we define the melting point of water as 273.15. That's a fixed point, and all other temperatures, however, have to be, that's just a ratio, then everything else. Okay, so what we do in the international temperature scale is people measure the melting point of gold using an ideal gas thermometer as accurately as possible, and that determines then what the melting point of gold is. Thereafter, we say gold melts at that temperature. So the melting point of gold is a secondary point. It can be measured to within about 1/100th of a degree. Now, and we have other, there's all sorts of fixed points. The melting point of antimony was one. These are generally fixed as things that are easy to measure accurately. Gold is easy to measure because it's inert, it doesn't oxidize, doesn't dissolve a lot of impurities, and so on and so on. So we determine things that can be determined accurately. In between the fixed points, the melting point of antimony, gold, and so on, for in between, we fix some sort of measuring instrument, like a platinum rhodium thermocouple. We do a calibration of the platinum rhodium thermocouple, millivolts versus temperature, to get as close as we can to what we think is correct, and then afterwards we say that's the absolute international standard. So this then defines the international temperature scale is defined in terms of fixed points. The melting point of gold is exactly 1085.92000000, and in between that and 0 Kelvin or 0 Celsius, you use a platinum 13.000% rhodium thermocouple, and this is your calibration table and so on. Okay, so now we have what we call the international practical temperature scale. Now suppose that we fixed up this international temperature scale and somebody finds 5 years later that the melting point of gold is not exactly 1000.29, it's 1000.26. If we went and changed that we should change the international temperature scale to be closer to the thermodynamic temperature scale, the trouble is that then people would know exactly what you meant. You report in a paper that I measured this temperature to be something. Well, what temperature scale were you measuring it on? Did you use the correction in 2007, or were you using what we thought was there in 2006? It would make it difficult to know exactly what we were reading in the literature. So we have to have an international temperature scale, even though we know it's a little bit wrong. We use it anyway so that everybody just knows what we're talking about. The differences are very slight, so it really doesn't make an awful lot of difference practically. But every 20, 30 years or whatever, when enough errors pile up, then the International Committee gets together and say, okay, we're going to come up with a new temperature scale. Okay, so this was the International Temperature Scale there's International Temperature Scale of 1927, International Temperature Scale of 48, 68, and 90. And I think there's been one recently. I haven't got it on this table, but now the changes are very, very small. Okay, and this shows you the equivalence. Okay, so as we go up in time, they're getting closer and closer to what the right value is. But now, so at low temperatures, the differences are really quite small. Even between 1927 and 1990, if you're around 700 degrees, we saw that it's off by about 0.6. So this means you're correct. You're reading an article that was written in 1948, and it says the temperature was 700 degrees. You know the real temperature on today's temperature scale is 700.6. you can make the correction. All right. So you should look at the date of you should have this table somewhere. If you're doing optimizations, you should look at the date of your article, and to be exact, you could make this change. Now you see, it really, within the accuracy of the sort of things you tend to do, the difference is not much. It might be a degree or so, but as you get to high temperatures, where it's harder to make accurate measurements, then you see the differences can actually be, if not large, at least worthwhile changing. Okay, so if you're talking about 2400 Celsius, around the melting point of some oxides, and you're using a paper written before around 1948, the difference can be 3 degrees, and you should make that change. Okay, so these are the international temperature scales. You can get these on the web. Just Google international temperature scales and you'll see the equivalents. Okay, and if you're doing oxide phase diagrams, you'll find some of the definitive work at oxide phase diagrams was done like back in 1920 and 1930. These were really good measurements, but the temperature scale can be off by 5 or 10 degrees something. Anyway, that's how the international temperature scale. Why don't we change it every minute? Because then we wouldn't know what we're talking about. This is changes often as necessary, but not too often. Okay, the differences are slight. If you get up to around 7,000 or 8,000 degrees, though, there can be pretty big differences here. It's really hard to measure these things. Now, there's other ways. It isn't always done with an ideal gas thermometer, because we can do it by spectra as well, and from spectra you can look at that. We try to get as close as possible as we can to the thermodynamic temperature scale. That's what we do. One final thing is that geologists, and if you're doing, a lot of you I think are doing oxide phase diagrams within all the, a lot of those diagrams are measured by geologists. And geologists are a strange crowd, and the geologists used they called it the International Geological Temperature Scale or whatever, but they did not buy into this thing. And they had a temperature scale which I think was consistent with the International Temperature Scale back about 1916, and they continued to use that right up to the 1950s and 60s, even though they knew that it was way off. Okay, that's how geologists did things. So you've got to be really careful if you're reading a paper from a Department of Geology or something, even if it's written up to the 60s. If they're using this crazy geological temperature scale, it can be off by quite a bit. We even back in the past found this out like 30 years ago or 25 years ago, when we did a lot of our oxide diagrams. We had to redo a bunch of them. They were 10, 15 degrees off from the international temperature scale. Okay. Anyway, that's temperature scales. So temperature is not an arbitrary thing. Temperature must be defined in terms of the second law of thermodynamics, otherwise the second law of thermodynamics doesn't work. There is only one temperature scale for which the second law of thermodynamics works. Now, these differences are not enough to really influence very much thermodynamic calculations and so on, but they certainly are enough to make it, not knowing what we're talking about, somebody measures the melting point today and finds it's 10 degrees different from what somebody measured in 1930, and it doesn't mean the guy measured it wrong, it just means he had it on a different temperature scale. Okay, let's continue with this thing. That was in section 2.3 or something. Okay, Gibbs energy. I define Gibbs energy as H minus Ts. All right, this is just doing a little more formally what I did. We had the equations 13 and 19. 19 is the definition of G. Equation 13 was the fundamental equation of thermodynamics. it wasn't. dH is dq plus vdp. Okay, du is dq minus pdv. H is u plus pv, so it follows that dH is dq plus vdp. Well, you can read all this. H is u plus pv. You differentiate that, you get dH is du plus pdv plus vdp. You plug that into this equation here, which is the first law, and you end up getting this equation, and I said before, if p is constant, dH is qp, and so on. So now if we take this equation for H, for dH, and we plug that into, take this equation, differentiate it, dg is dH minus TdS minus SdT, and so on, you fiddle around and you end up with this equation here. that dG is dQ plus vdP minus TdS minus SdT. General equation. Consequently, for a process occurring at constant T and P in a closed system, dP is 0, dt is 0. Okay, so we have dG is dH minus TdS. This is what I did last day, but done a little bit more mathematically rigorously. The ds surroundings is minus dQ over T. Assume the surroundings is a heat sink, which sees only a reversible transfer of heat. And then you end up that dG is minus dds total is less than 0. Is a special form of the second law at constant temperature and pressure and constant number of moles. So for a system at constant T and P, with a closed system with a fixed number of moles, for any spontaneous process, dG will be less than 0. When the system's at equilibrium, dG will be equal to 0. Okay, so this is a special form of the second law for a process occurring in a closed system at constant T and P. This is the most useful form of the second law. I'll show you why. An objection might be raised that this only applies when the surroundings are at the same temperature as the system. We went through all that. If the temperatures at a different surroundings, you consider that different temperature, you consider that to be a different process. Okay, so we went through all of these things. I did these examples. What I was looking for. Okay, if the actual process is reversible, that is, if the system is at equilibrium, then dG equals 0. So this is what we mean by the minimization of Gibbs energy when we're using a program like FACSAID, Solgas, minimizing the Gibbs energy. We take a system that's, say, not at internal equilibrium. We calculate the Gibbs energy of the system. We then make a change in the internal properties. We make a little bit more of one phase, a little bit less of that phase. We change the composition. Any change that decreases the Gibbs energy is heading towards equilibrium. Okay, so we reach a point where dG is equal to 0, and that simply means that we're now at a point in the system that any change we make to the system, any way we move a little bit of material from this phase to this phase or change things, it'll raise G. So anything we do is going to increase G, so now we're at the minimum of G, so now the system's at equilibrium. And that essentially is what Solgas and all equilibrium thermodynamic algorithms do, is they take a system that's not at equilibrium, they approach equilibrium at constant T and P by various numerical methods to find the point where the G is at a minimum. When G is at a minimum, the system's at equilibrium. Okay, let's look at a few things about chemical reactions. So again, this is trivial stuff, but we're talking about notation now. Okay, consider the question of whether silica fibers and an aluminum matrix will form mullite. So this is the reaction we're interested in. So this is pure silica, pure aluminum, forms pure silicon plus pure mullite. No solutions, just pure solids. If the reaction, you put these four things together and you allow the reaction to move a little bit to the right to form dxi moles of mullite. So it moves just slightly to the, displaced slightly. Then from the stoichiometry of the reaction, if you form dxi mole, if you form 1 mole of mullite, you'd form 9/2 moles of silicon. You'd form -6 moles of aluminum and -13/2 moles of, so these are the change in the number of moles of the reactants and products as the reaction displaces slightly. So since the four substances are essentially miscible at 500, their Gibbs energies are equal to their standard molar Gibbs energy. So the G zero, small g because it's molar, the 0 up here means it's the standard chemical potential or the standard Gibbs energy, meaning it's the pure, if it's a solid or a liquid, it's the pure material. If it's a gas, it's the pure gas at 1 atmosphere partial pressure. Okay. The Gibbs energy of the system then varies as follows. As you displace the reaction by dxi, there's a change in dg. The change in dg is equal to, you're forming then if you form dxi moles, you're forming g, this is the change in energy per mole of mullite produced times dxi moles are produced plus 9/2 silicon and so on. This is the change in Gibbs energy accompanying the displacement by dxi, but this is simply the difference of, this is the Gibbs energy of the products minus the Gibbs energy of the reactants weighted by the stoichiometric factors, which is simply delta G standard for this reaction. Delta G standard for this reaction is the molar Gibbs energy of the products minus the molar Gibbs energy of the reactants. Okay, so we see then that this is the criterion. We always say for the reaction, you often see this produced delta G. Okay, maybe this is a minor point mathematically. We say, well, for this reaction, delta G0 molar is minus 830. So if 1 mole, 13½ moles of silica and 6 moles of alumina react completely to form this and this, then that's delta G0 and it's negative and so on and so on. And people always say, well, what happens if it doesn't react completely? Well, it doesn't react completely. dg d psi, any slight displacement changes gives you a negative Gibbs energy. So the Gibbs energy delta G0 is negative. That means the displacement of the reaction to the right will diminish G, so the reaction is spontaneous to the right. Delta G, the formation, and hence the reaction will proceed spontaneously. In this case, equilibrium will never be attained, and the reaction will simply proceed till it's complete. Okay, now suppose we have an equilibrium involving a gas phase and an ideal gas mixture. PV is nRT. Furthermore, the partial pressure of each gaseous species is given by Pi, or Pi is the partial pressure, Ni is the number of moles of that particular gas. And this is Dalton's law then. If this is true, if total pressure is sigma Pi, then that's Dalton's law, as we said yesterday, because for an ideal gas it isn't necessarily true. It can be shown then that G is, for an ideal gas, the Gibbs energy of the ideal gas not in the standard state, because this is not at 1 atmosphere, is equal to the Gibbs energy at 1 atmosphere. G naught I is the Gibbs energy per mole at 1 atmosphere plus RT log P. Okay, and this term is the entropy change, remember? So delta G, let's say I take a gas, I take whatever oxygen at 1 atmosphere, at P0 equals 1.0 bar. And I go to form oxygen gas at Pi, at some other pressure Pi. Okay, for this reaction, and it's an ideal gas. Okay, delta G is delta H minus T delta S for this reaction. What is delta H for this reaction? Delta H, this is temperature equals constant. So we have a constant temperature, the gas is changing its pressure, changing its volume at constant temperature. Delta H is delta U plus delta PV. What's delta U? Ideal gas, constant temperature, 0. What's delta PV? PV is nRT, T is constant, 0. So there's no enthalpy when you change the pressure of an ideal gas, which is reasonable. In an ideal gas, the molecules are not interacting. It doesn't matter how far apart they are, there's no change in energy. If gas is not ideal, you put them closer together, you form incipient bonds. So delta H is 0 for the, okay. What is delta S for this reaction? Delta S is Q reversible over T. Okay, Q reversible is RT log P over P0. We did that already. Next, the heat of reversible expansion of an ideal gas. Right. Actually, I think it's negative, right? If you expand, it's negative. If you expand the gas, then this ratio is positive, and you got a negative. You got a. The total entropy has to be negative because it's expanded. Okay, remember delta. It's not a mystery to anybody, I see. Okay, we've used this many times. The delta W reversible is RT log P over P. Q reversible is minus RT log P over. So we then that's delta. This gives us delta S. We have delta H. We say delta G is delta H minus T delta S. So delta G for changing the pressure of the ideal gas is RT log P over P naught. Okay, so delta G is what now? Delta G for this reaction, delta G for this reaction is the Gibbs energy of the gas at the pressure P minus the Gibbs energy of the gas in its standard state. Okay, so that then ends up giving us this equation here. So G minus G naught G equals G naught plus RT log P. Sometimes when I do this on the board I miss a sign somewhere. I think it's okay. If I miss a sign, you're to ignore it. Okay, now the difference is this is P over P naught. Here I've written P. Why not P naught? Because P naught's the standard pressure is 1 bar. But it really is P over P naught. Okay, and some people say, what are the units of P? Well, because they say, well, delta G depends on what you use for P. If you use bars or millimeters of mercury or atmospheres or something, you're going to get a different G. Well, no, you aren't, because it's P over P naught. It's just a ratio. Okay, the standard state is 1 bar. The standard state is 760 torr. So if you convert P to torr, then you have to put in the P naught and put it in torr, and you still end up with the same. Okay. Anything that's inside a logarithm must be dimensional. When people say, what's the equal to, well, I'll come to this in a minute. What are the units of the equilibrium constant? There are no units to an equilibrium constant. If it's RT log K, you can't have units. Okay, so this is the Gibbs energy. So what this means is, let's think, is this reasonable? As I increase the pressure above 1 atmosphere, this means the Gibbs energy goes up. Things trying to expand will have a lower entropy. Okay, or therefore a higher G energy. Higher entropy, lower Gibbs energy. All right, so now let's consider a gaseous mixture. So we have a mixture of hydrogen, sulfur, and H2S, and these are the partial pressures of them, and the gas can react. And let's do the same thing we did before with the molite thing. We have the formation of two dxi moles of H2S, so minus dxi moles of sulfur and minus 2 dxi moles of hydrogen as the reaction is displaced towards the right. And then I run again, dg dxi is 2gH2S minus G minus GS2. But now for each of these things, before I just said that the G was equal to the standard Gibbs energy, but now we're changing the Gibbs energy of H2S, but the Gibbs energy of H2S has to be given by this expression. Okay, so I substitute that expression. So for H2S, for GH2S, I substitute G standard H2S plus RT 2 log PH2S. So for each of the G's here, I substitute the equation G naught plus RT log P. And I get delta G, then this is equal to delta G naught plus RT log of this ratio. And that's the Gibbs energy change. I don't write a delta G 0 because this is the Gibbs energy change for that reaction as written for those given partial pressures. And this is another source of confusion. Okay, I'm putting H2, H2S, and sulfur all together in a container. So I have a box here, a container, and I have a certain H2, I have a certain PS2, and I have a certain PH2S. These are not necessarily the equilibrium values, they're the present values. Is the reaction going to start going now? In which way? One way or the other? These are not the equilibrium values, so the system's going to try to reach equilibrium. Which way will it go? Well, if it goes to the right, then it will go to the right if delta G is negative. So delta G is delta G 0. Delta G is the delta G for that reaction. The reactants and products are not in their standard state. They're not at 1 bar. Okay, I think will keep coming up. It's a delta G. So I calculate delta G 0. Now delta G 0 I can get from tables of thermodynamic properties for the pure materials. And I plug in here the partial pressures. And then I determine whether delta G is positive or negative. If it's negative, then this reaction will proceed to the right with formation of H2S. Or if it's positive, it'll proceed to the left with formation of H2 and S2. As it proceeds, let's say it proceeds to the right. I plug in the partial, I take delta G 0 from the literature, I plug in the partial pressures that I have in the system, which are not the equilibrium partial pressures. This, by the way, is not the equilibrium constant. This is just the ratio of the partial pressures that happen to be there now. Equilibrium constant is the values at equilibrium. These are not at equilibrium. I calculate delta G is negative, so the thing proceeds to the right. But as it proceeds to the right, the pressure of H2S increases. The other two pressures decrease, so this term over here becomes more and more positive. Okay, so delta G becomes less and less negative until you reach a point when the system's at equilibrium. Now any further change gives you a dG equals to 0. Okay, so the system moves to the right, increasing the pressure of H2S, decreasing the pressure of the products. This term becomes more and more positive. Delta G becomes less and less negative until it reaches equilibrium. Then you're at equilibrium. Okay, and that's the minimum of the Gibbs energy. Now, when you're at equilibrium, delta G equals 0. So if I'm at equilibrium, I'll put delta G equals 0, and then this equation gives me delta G 0 equals minus RT log of pH2S squared over pH2 squared times PS2 at equilibrium. Sorry to stress this point, but it's amazing people don't have a problem. Delta G0 is minus RT log of this ratio, where this is the ratio when the system's at equilibrium. Not any old ratio that happens to be in there. This is the one and only ratio at a given temperature T for which delta G will be equal to 0. So this ratio at equilibrium is called the equilibrium constant. Okay. This ratio that's in here in general is not the equilibrium constant. That's just whatever non-equilibrium pressures you happen to have at the moment. When that ratio is equal to the, when this ratio of pressures is such that delta G equals 0, then this equation is true, and then this ratio is called the equilibrium constant. So we end up with the famous equation, delta G0 is minus RT log equilibrium constant, and people will then say that delta G0 is the Gibbs energy change at equilibrium, which is wrong. Delta G0 is the Gibbs energy change from the standard state. Delta G0 is equal to the Gibbs energy change of 2 times the standard Gibbs energy of H2S minus 2 times the standard Gibbs energy of hydrogen minus the standard Gibbs energy of sulfur. And these are the Gibbs energies when all the partial pressures are 1 atmosphere, when the system is certainly not at equilibrium. Okay. Delta G0 is the standard Gibbs energy change when all reactants and products are in their standard state, which means partial pressures of 1 atmosphere. That's not at equilibrium. In that case, delta G equals delta G0 plus 0. Then the action shifts until the equilibrium, until delta G becomes equal to 0, etc., etc. So delta G0 is not the Gibbs energy change at equilibrium. The Gibbs energy change at equilibrium is necessarily 0. Okay, and you look at this expression here, delta G is delta G0. We'll see people writing delta G is delta G0 plus RT log K. That's also nonsense. Delta G is delta G0 plus RK2 log of the actual ratio, not K. Okay? K is the ratio that makes delta G equal to 0. That's the equilibrium constant. All right, what are the units of the equilibrium constant? In this particular case, this is the equilibrium constant here. So the units are, say, atmosphere squared over atmosphere squared, atmosphere. So the units of K are atmospheres to the minus 1. Is that correct? The units of K are atmosphere, this or bar, let's say bar squared over bar squared bar. So the units, these cancel, the units. Equilibrium constant is bars to the minus 1. Which is crazy because you cannot, anything within a logarithm must be dimensionless. And the reason is that it's this simplification we make. We really should not be writing P, we should be writing P over P naught every time. Okay, so the equilibrium constant for this reaction, the real equilibrium constant for this reaction is equal to pH2S over P naught, H2S squared, divided by pH2 over P naught, H2 squared times P sulfur over P sulfur, P naught. Okay, so it's only ratios, so it's dimensionless. But if the P naughts are all 1 atmosphere, because that's the way we choose it for convenience, then we set these, we just don't put these terms in our equation just to make it easier to write, but they should always be there. And if the pressures, and so you can only, if you write the equilibrium constant this way, then those pressures have to be in bar. If these pressures are not in bar, then it won't work, because then you have to divide by whatever your standard state. If you have partial pressures in torr, 760 torr to an atmosphere, then you have to, pH2S is pressure divided by 760, in other words, the pressure. Okay, so the equilibrium constants are dimensional. Okay, these are things that, you know, like the first year course in thermodynamics, but find people saying this all the time, and it's important. Okay. So for the equilibrium state, K is the equilibrium, I said all that. Okay, any questions about that? As a further example, consider the possible precipitation of graphite from a gaseous mixture of CO and CO2. So you have a gas consisting of CO and CO2 in a container, and carbon might precipitate out of the gas. So we do exactly the same thing, and we see that delta G, or Adiabatic say, is delta G, which is delta G naught plus RT log. And in this particular case, the carbon is pure carbon, pure graphite. So the equilibrium constant now only, for the moment, since the carbon is pure graphite, it doesn't figure in the equilibrium constant. So you just have PCO, you just have the gases in the equilibrium constant. And if this, so there will be an equilibrium constant RT log K. Okay, what I've written here, I've written it a little different way just to show the delta G, the dg psi, which is delta G. Okay, and the delta G is delta G naught plus RT log of the actual ratio. This is maybe another way. Well, let me write one last thing which we could have written here, even with respect to the previous reaction. Even with respect to this reaction, we have delta G is delta G naught plus RT log of the actual ratio. With delta G is 0, then it's RT log K. So I could also write, of course, that delta G is delta G 0 plus RT log of the real ratio. But RT log K, so this is minus RT log K plus RT log of the ratio, real ratio. So simply another way of looking at it. RT log of the actual ratio minus RT log of the equilibrium ratio. When the actual ratio is equal to the equilibrium ratio, delta G will be 0. Delta G then is the driving force. It tells you the distance you are from equilibrium. If the real ratio is greater than the actual ratio, the reaction will go to the left. If it's less, the delta, because delta G will be positive. If the real ratio is less, then the reaction will go to the right. Alright, so when I write the same thing here, the carbon plus oxygen, once again the CO, the carbon doesn't figure in it, but if CO, if the partial pressure, if the equilibrium, if the real ratio, or real ratio is less than the equilibrium constant, then the precipitation will occur in order to decrease G. Real situations, of course, are more complex because you have several possible reactions going on together. So if you have, you want to see whether silicon, this is a chemical vapor deposition, you have a vapor of silicon tetraiodide gas, and you want to decompose the silicon tetraiodide gas to deposit silicon on the substrate, chemical vapor deposition of semiconductors. So you're hoping your silicon tetraiodide gas will deposit silicon and form iodine gas, but you have other things to consider too, that the silicon tetraiodide will dissociate to form silicon diiodide gas, that the iodine gas will partially dissociate to form monatomic iodine, and the whole system will be at equilibrium when all three of these reactions are at equilibrium, or when the entire Gibbs energy of the system is minimized. There's two ways of doing this. I won't write it all out. The old classical way is you write an equilibrium constant for every single reaction, as we did here, equilibrium constant, and then you find the ratio of the various partial pressures of the various gases, keeping the mass balances into account, so that all three equilibrium constants are satisfied. When you find a set of partial pressures for all the gases that satisfy all three equilibrium constants under the mass balance constraints, then the system's at equilibrium. Another way of doing it, when we have the computers now, is what you do is you simply minimize the total Gibbs energy of the system. You find the Gibbs energy that minimizes the entire, okay, you would have the Gibbs energy of the system would be then the number of moles of I times total Gibbs energy of the system is the sum for all possible species, and the species would be silicon tetraiodide, silicon diiodide, iodine gas, and iodine. This is the number of moles of every gas times the Gibbs energy of that gas plus RT log partial pressure of that gas. Okay, so you're trying to minimize the total Gibbs energy of the system. The partial pressure of the gas, then, partial pressure of the gas, and you have to do this subject to the mass balances, that the number of moles of silicon tetraiodide plus the moles of silicon diiodide, etc., equals the total number of moles of silicon in the system. So you try to minimize it, find the number of moles of each particular species that minimizes the total Gibbs energy, given the mass balance, how much silicon iodine you have in the entire system. Okay. And this is how the Gibbs energy minimizer works. But once you've found the number of moles of every particular gas, and silicon as well, that minimizes the Gibbs energy, if you were then to put those mole numbers back into the equilibrium constants, you'd find that all the equilibrium constants were satisfied. So satisfying all the equilibrium constants or minimizing the total Gibbs energy, same thing. I'll maybe do that a little bit more later, but okay, so we say that, in the old way you would write out all the equilibrium constants and then try to solve all the equilibrium constants to find the overall equilibrium, or you can minimize the total Gibbs energy, in both cases subject to the mass balance constraints. Either way, you end up with the equilibrium state, and that's the same equilibrium state. Is that clear, or should I go into more detail? Was that too fast, or?
Maybe later with more examples.
To do the example, I'm not sure I could do the general derivation right now without thinking about it for a couple of minutes. Okay, well, you see here you have to, in this example then, okay, Ni is the number of moles of each particular species. Okay, plus we'd have, this is all the I gas. So I involves the silicon tetraiodide, silicon diiodide, I2, and I are the gaseous species. So this is the Gibbs energy, where Ni then is the number of moles of that particular gas. So N SiI4 is the number of moles at SiI4 in the system, and so on. G0I is the standard Gibbs energy of silicon tetraiodide, and this is the partial pressure of silicon tetraiodide. Plus that we have to put in the solid, so this would be N silicon times G naught silicon. Put that solid so you don't have to put in the RT log P. Okay, so that's your total Gibbs energy of the system. And in that Gibbs energy of the system, I could also write that the partial pressure of I is equal to the number of moles of I divided by N total of the gas. So this would be sigma Ni over the gas times P total. P total is the total pressure of the system. This is the mole fraction of number. This is Dalton's law. The partial pressure is equal to the number of moles of I over the total number of moles times P total. That's Dalton's law. Okay, so I have to fix the P total. So, okay. All right, so now then I have a certain mass balance. So these, I have to minimize the Gibbs energy. This simply then substitutes in here. Okay, so now if I have P total, I get the G0s. I get the G0s from the thermodynamic tables. Okay, and I'm trying to find the number of moles of each gas. Okay, how far? This whole thing is going to shift around until the whole thing reaches equilibrium. At equilibrium, you'll have a certain number of moles of silicon tetraiodide, a certain number of moles of SiI2, and so on, a certain number of moles of silicon. This could be 0, by the way, but number of moles of silicon could be 0, no silicon deposits. And what you're trying to, and the partial pressures then are equal to this. That's, say you fix the total pressure to be something like. Okay, so the system will, you're trying to find what are the number of moles of each of the materials when the thing's at equilibrium. Now you also have mass balance restrictions. How much silicon and iodine did I put into there to start with? So I will have N silicon total, and I will have N iodine total that were put into the system initially. And it's a closed system, so they remain constant. If I started off with 1 mole of silicon tetraiodide, then of course the number of moles of silicon is 1, the number of moles of iodine is 4. This is a total mass balance. Hence, I would say that the number of moles of silicon I4 plus the number of moles of silicon I2 plus the number of moles of silicon, those are all the silicon containing species, equals N silicon total. And I would say the number 4 times, let's see, 4 times the number of moles of SiI4 plus 2 times the number of moles of SiI2 plus 2 times the number of moles of I2 plus the number of moles of I equals Ni. Total. Those are your mass balances. Okay. The total amount of silicon in every species is equal to the total amount of silicon. The amount of iodine in every species equals 2. Okay, so I have to minimize the Gibbs energy under these are called constraints. Actually, my constraints would be mass balance constraints, closed system, total pressure constraint, and then I try to find the number of moles Ni of every species that minimizes the Gibbs energy. That's what the Gibbs energy minimization program does. You can set other constraints. For example, you could say not the total pressure is constant, but the total volume is constant. Okay, in that case you would have PV is N total RT. The volume, total volume would be constant, and your total pressure then is given by this equation. But N total is given by a total number of moles. And total then is the number of, well, it's the number of, total number of moles of, sorry, total number of moles of gas and total gas. Okay, so we have additional, this is your constraint. The total number of gases is fixed. RT, volume is fixed. That gives you P, which you can substitute back into here and do the, there you go. Okay, the different constraints. Still, it's the same thing. Given enough constraints to properly constrain the system, generally mass balance and a total pressure or total volume constraint, you minimize the total Gibbs energy, and the mole numbers you get, Ni here, are the mole numbers at equilibrium. That's how fact stage works. Now, this is important. Say I fix the total, that's fine if I fix the total pressure. Suppose I fix the total volume. Now, I'm trying to minimize this because it causes confusion. Now, fact stage minimizes the total Gibbs energy, but remember, dg is less than 0 is the second law at constant T and P. Okay, I said that dg at T and P is less than or equal to 0 is a special form of the second law for a reaction that's going at constant T and P. But now the reaction is not going at constant T and P, it's going at constant T and V. So I start off with my silicon tetraiodide in the box, okay, and I go towards equilibrium, keeping the volume constant, okay, but I should not be minimizing the Gibbs energy. I should be, actually, I'll show you in a minute, I should be minimizing the Helmholtz energy. Okay, I could actually, why don't we do that now? It only takes a second. Sorry, Jim. I want to just put a cover over that one. Okay, we define the Helmholtz energy A, which is another auxiliary function, is defined as U minus Ts. Okay, remember G was H minus Ts. A is U minus Ts. So delta A at temperature and volume constant is equal to delta U at temperature and volume constant minus T delta S. Okay, but remember for a process at constant volume, delta U is equal to the heat. So this is equal to Q at constant T and V minus T delta S. Okay. When we did the G is H minus T S, we said delta G at constant T and P is equal to delta H at T and P minus T delta S, and delta H was equal to Q. And this was minus T delta S surroundings. Okay. Now Q, T, and V is minus T, so this was equal to minus T delta S surroundings minus T delta S equals minus T delta S total. So at constant T and P, delta G is equal to minus T delta S total, which is the general form of the second law. Delta S should be positive. If T and V are constant, then delta A is equal to delta QTV. At constant at constant volume, the delta U is equal to Q. Okay, as we showed before, that's the principle of the bomb calorimeter. And now this is minus T del S surroundings, minus T del S, which is minus T del S total. Okay, so at constant T and V, you should be minimizing delta A. A is called the Helmholtz function. G is the Gibbs function or the Gibbs free energy. Helmholtz is the Helmholtz function or the Helmholtz free energy. It's also called the work function. No reason to talk about why that's the case. G is for Gibbs. A is for Arbeit, which is the German word for work. Okay, so we should be minimizing the Helmholtz Gibbs free energy, not the Gibbs free energy. Okay, so different constraints. Now, why don't we do this? We don't do this because we already have this nice expression, delta G is delta G naught plus RT log P, expressing the Gibbs energy in terms of pressure and everything. It's easier to express things, then you'd have to express everything in terms of volume. You'd have to rewrite your equilibrium constants, your delta G's at constant volume. Okay, and especially when you're getting into things like solutions, the sort of minimalization that we do in FactSage, then you would have to be expressing not things in terms of pressures and temperatures, you have to express everything in terms of temperature and volume, you'd have to have constant volume heats of mixing and so on. It's just much more convenient to do things at constant pressure. Okay, so how do we do it? Well, the way FactSage does it is, if I tell it I want to do this at a constant volume, it guesses a pressure, minimizes the Gibbs energy at constant pressure till the whole thing's at equilibrium, and then says, guesses a pressure of 1 atmosphere. Say I want volume equal to 1.0 liters. I guess the pressure of 1 atmosphere. I minimize the Gibbs energy at constant T and P. The system's now at equilibrium at 1 atmosphere. Now I go back here and I calculate the volume. If the volume's too big, obviously my pressure was too low, so I decrease the pressure by an increment and I redo the calculation at a new pressure. I reach a new equilibrium, minimizing dG each time, until after I reach equilibrium, the volume that I calculate is the one I want. That's easier than trying to reformulate the equations every time. Okay, so that's how it works under different constraints. No matter what the constraints are, Sol gas, which is the algorithm at the basis of equilibrium in FactSage, Sol gas, whatever your constraints are, like constant volume or whatever, Sol gas will guess constant temperature and pressure, will minimize it. Even if the temperature isn't constant, you want to do an adiabatic reaction. It'll guess what the temperature is going to be at equilibrium, do the calculation, and then see if the temperature is too high or too low, change the conditions, try it again until you end up with something that's right. Okay, so is that clear how it works? Okay, so we can write all this kind of stuff, but it isn't really all that terribly useful because that's not the way our algorithms really work. The algorithms really pick T and guess the temperature and pressure. Okay, how do we know whether to go up or down? Well, okay, I calculate it, I guess the pressure of 1 atmosphere, I let the thing reach equilibrium, then I calculate whether it's at equilibrium. If the volume's now too big, bigger than 1 atmosphere, well then the pressure has to be higher. If it's too small, the pressure's already too high, the pressure has to be reduced. Okay, so you do it incrementally until you narrow into the final answer. Okay, that's how you do it. If you were trying to do an adiabatic, a flame temperature, you mix, as we did the other day, in methane and oxygen, you let the thing go adiabatically. What is the final temperature of the flame when the thing reaches final temperature? You're trying to calculate equilibrium at this higher temperature, so you would guess what the higher temperature was, let the thing reach equilibrium and see if it was actually adiabatic or not. If it wasn't, then you go higher or lower until you ended up with the temperature. Okay. So that's why this is what I said then, that earlier, that this is the most practical way of expressing the second law in terms of writing computer programs to minimize Gibbs energy, to find equilibrium, is because this is generally it's easier to express thermodynamic properties of materials and solutions in terms of temperature, pressure, and composition than in terms of other variables. But even if it weren't easier, we like to do it just one way, not several different things. So everything is written in terms of Gibbs energies, thermodynamic properties, and the tables are all expressed in terms of TP and composition, and so we can use that. It's not really a restriction on what we do. They say, well, you reached equilibrium at constant T and P. I still have the problem. Okay, you've reached equilibrium at constant T and P, but if you'd reached equilibrium at constant T and V, you would have gone along a different path. Well, no, you've reached equilibrium, now the system's at a T, P, and V. It doesn't matter how you got there. When it's at equilibrium, it is at equilibrium. It isn't going to suddenly not be at equilibrium because you're going to change the variable. It doesn't matter how you got to equilibrium. Once you're at equilibrium, the system's at equilibrium now. So, okay, so that's why we do it. Let's just do one diagram now. Figure 9. Because I want to see if this thing works here. Okay, that's figure 9. That's called the predominance diagram for the copper sulfur oxygen system. You've all seen this, I presume? No? Oh, I'm sorry. Thank you. Copper sulfur oxygen system. Everybody know what a predominance diagram is? Anybody who doesn't know what a predominance diagram is? Okay, well, the predominance diagram then is just a graphical representation of some of the chemical equilibria. So this means if I take a system, I take a container here, I put in a certain PSO2, I put in a certain PO2, and I put some copper down here, and I let the system reach equilibrium. What material do I find at equilibrium in the system? So I impose a small amount of copper and I impose an equilibrium SO2 and oxygen pressure on the system, let the system reach equilibrium. Okay, so this is log PO2 at equilibrium, this is log PSO2 at equilibrium, and this tells you what phase field you happen to be in. Okay, so if you happen to have at point Z, if you have a PO2 of 10 to the minus 7 and a PSO2 of 10 to the minus 2, if I put some copper in there and I impose PSO2 and PO2 equal to these values, the copper will oxidize and at equilibrium I'll have Cu2O. If I keep the SO2 pressure constant and increase the oxygen pressure, I move over here and now I have CuO and so on. If I'm exactly on this line, I will have two phases. I will have Cu2O and CuO. Okay, the only way to have those two phases at equilibrium is if the oxygen pressure is exactly equal to that value. The only way to have metallic copper and Cu2S at equilibrium is if the SO2 and the oxygen pressures are exactly along that line. The only way to have these three phases at equilibrium is if the oxygen pressure is exactly at that point. You will not find three solid phases in that system unless you have exactly that PSO2 and PO2. Okay, that's called a triple point. These are called the two-phase lines. It's important to remember when you're interpreting this diagram, the most common error that people make when they're interpreting the diagram is they think that PSO2 and PO2 is the total pressure in the system. Okay, so they say, look, if I put a PSO2 of 10 to the minus, of less than 1 atmosphere, say I put an SO2 pressure of 10 to the minus 1, and I put an oxygen pressure of 10 to the minus 18 or something. Okay, so I'm at this point here. Then I'm going to have Cu2S. Okay, so that's very easy to do. I have the total pressure will be less than 1 atmosphere. I have PSO. This is the partial pressure of SO2 is 10 to the minus 1. And the partial pressure of oxygen is 10 to the minus 18. So I easily can fix that in my system, and I'll have Cu2S. The trouble is SO2 and oxygen are by no means the only gases in the system. The most important other one is sulfur, so you'd have SO2 gives you 1/2 S2 plus oxygen. And if you have a very low partial pressure of oxygen, you're going to have a very high partial pressure of sulfur because the equilibrium constant is equal to PO2 times PS2 to the 1/2 divided by PSO2. Okay. All right, so what happens is the total pressure, the error people make is assuming that the total pressure is the sum of these two axes, and it's not. And at this point here, you will find that even though PSO2 is low, PO2 is very low, PS2 from this equilibrium constant is now greater than 1 atmosphere. So this is an unrealizable point unless you go to very high pressures. So on this line we can draw this crossed line, which is the P total line. P total is simply solving this equation. You simply solve that. For any given PSO2 and PO2, you can calculate PSO2, PS2. Well, to do it right, you're calculating PS3, PS4, PS1 as well, and summing the whole thing up. Okay, so in this region here, it's mainly sulfur is the main part of the gas. In this region, the total pressure is pretty much equal to the SO2 pressure. So in this region, the gas consists mainly of SO2, and over here, the gas consists mainly of oxygen. Okay, and that's the total pressure line, which is the realizable region. Now, this is the metallurgy of copper, is that it's possible at P total is 1 bar to take Cu2S, less than 1 bar to take Cu2S, go over to form copper without forming copper oxide. But if you go up here, then you would go directly from Cu2S to copper oxide. Okay, so we have 1-phase regions, 2-phase lines, and 3-phase triple bonds. All right, do I just delete it now? I'm not used to this damn thing. That's what I want. Okay. Why do they do it this way? It's so stupid. Okay, so why do we have coexistence of 2-3 solid phases? So if you have a line, there's a line separating Cu2O and CuSO4 domains. So on the diagram, there's a line between Cu2O and CuSO4. Along that line, this, let's see if I can find the line. Cu2O and, what did I say, CuSO4? That's this line. Along this line, Cu2O and CuSO4 are in equilibrium. So Cu2O and CuSO4 are in equilibrium on that line. Why is that a line? Okay, along that line, this reaction is in equilibrium. Cu2O, CuSO4 are in equilibrium with the gas phase. Therefore, along that line, this equilibrium constant, log K, the equilibrium constant is satisfied. So the equilibrium constant is constant along that line, okay, where the 2 phases are in equilibrium. Okay, the equilibrium constant is when they're in equilibrium. The axes are the equilibrium partial pressures. We say that the line is the equilibrium line, so equilibrium constant is satisfied along that line. If you take log K, delta G0 is minus RT log K. Log K, okay, is minus 2 log PSO2, minus 3s log PO2 is constant. So along that line, the 2 of them will be equal. There will be an equilibrium along the line. If we pick any value of PSO2, there's only one value of PO2 for which those 2 phases can be in equilibrium, and that will exist along that line. And the slope of the line is then equal to minus 3/2 over 2, which is minus 3/4. So you get this line here has a slope of minus 3/4. Clearly, if you have, so along this line you have these 2 phases can only exist along this line, these 2 phases only along this line, these 2 phases only along this line. Clearly the point of intersection of those 3 lines is the only point where all 3 equilibrium constants are simultaneously satisfied. So we have a triple point. You cannot have more than 3 condensed phases at equilibrium at one time. You can't have 4 lines coming together. Okay, those are straight lines as long as you have an ideal gas. Remember the equilibrium constant, when we determine the equilibrium constant as a ratio of partial pressures, we've assumed ideal gas behavior. G is G0 plus RT log P is only true for an ideal gas. Otherwise, there will be a slight deviation from those lines. Okay, so that's that kind of predominance diagram. Does that Everybody happy with that one?
Can I ask a question?
Yep.
How usually do you define the P total, like this line, the collapses?
Oh, well, for every reaction, for this, well, let's assume that you have a reaction. You have SO2 produces 1/2 S2 plus O2. So for that reaction, there's a delta G0, which I can look up in my tables. Delta G0 is minus RT log K, so I can calculate K. Okay. Then I have K. I know what K is. I pick a point. I pick a value of PO2 and a value of PSO2, whatever. At this point here, I say PO2 is 10 to the minus 7, PSO2 is 10 to the minus 2. Okay, so I put in here PO2. I put PO2 is 10 to the minus 7, I put PSO2 is 10 to the minus 2, and I can calculate PS2. Okay, so PS2 can be calculated. Then I take another reaction, SO2 produces 1/3 S3 plus oxygen, and for this one I have another equilibrium constant, and from that I can calculate pressure at S3. I do this for all the gases, and then I say the P total is equal to PSO2 plus PO2 plus PS2 plus PS3 plus, and I calculate the total pressure. And this is the line along which the total pressure will be 1 atmosphere.
There is always one line in the predominance
And I'll be
diagram.
1 line at 1 atmosphere. Now you can plot diagrams the other way. Even for copper, sulfur, oxygen, I could plot log PS2 versus log PO2, and a diagram will look a bit different. Then you don't see PSO2. Okay, and then the diagram will be distorted, and there'll be a total pressure of 1 atmosphere line. Okay, so that's how you calculate it. I got any other questions with that? I did get diverted back a minute ago talking about the Gibbs energy minimization, and I forgot what I was actually trying to do. The example with the silicon tetraiodide, I wrote the whole equation to try to minimize the Gibbs energy. G is sigma Ni, etc., and I showed all the constraints. That's the way the computer program does it. The way you would have done this in your thermodynamics course, maybe without the computer program, is you would have taken every one of those reactions back there. For each one of these 3 reactions, I would write K for the first reaction is equal to PI2 squared over, it's equal to PI2 squared. K2 is equal to PI2 times PSII2 divided by PSII4, and the same for K3. Let's put it this way, all of these 3 Ks I can determine from delta G0 is equal to minus RT log K. Okay, so for each one of these 3 reactions, I can calculate, I get delta G0 from the literature, and I can obtain numerical values for each of these K1, K2, and K3. If I were then to take my result from FactSage, I would put this problem into FactSage with the constraints that I said, and I solve it by minimizing the Gibbs energy. And then I said after you solve it by minimizing the Gibbs energy, you'll get the equilibrium number of every species, and from that you can calculate the partial pressure of every species. That's the way it's done, by minimizing the total Gibbs energy, as I showed you. If you then take those partial pressures that you get from the output of FactSage and you put them into these equations, you will find that these equations are satisfied. If FactSage, which was minimize the Gibbs energy, gives me a partial pressure of I2, SII2, and SII4. I put those partial pressures in this equation, and I calculate K2. That's the K2 that I get from the literature. So minimizing Gibbs energy is the same thing as satisfying all the equilibrium constants simultaneously. It's not a different thing. And a nice little thermodynamic exercise is maybe you might convince yourself that that's true. But when I minimize the Gibbs energy, I in fact have solved all the equilibrium constants simultaneously. Actually, In the old days, before we had big computers, back prehistorically, this is the way you actually solve the problem, because this was actually, if you're going to do it with a hand calculator and paper and pencil, this is actually easier than minimizing. Minimizing gives energy is easier algorithmically, but requires thousands of calculations to narrow in, because it's a numerical method. This way was a faster way. Nobody does it that way anymore, but it's the same idea. I forgot what I was going to say, but that's okay. Any questions? Let's take 10 minutes to break.
Turn it off now, anyway.